share screen. Let's share the PowerPoint. And there's my little present guy. Okay, so I wanted to show you this weird little alternative form of the rate equation. It's not a big deal. I just want you to know what it is in case it shows up. It's just a matter of like knowing what the equation is and what it does, and you just write down some version of it or use it. It would be a really small part of a question, but I just figure it's relevant. We might as well mention it. These integrated rate laws are a much bigger deal. This is what shows up on this Kinetics FRQ that I've got for today. And then I just wanted to mention the one last thing that's like a really big part of kinetics that you should know is the energies of the reaction. It shows up in graphs with activation energy. I'm gonna post an assignment material on that. You can let me know if you wanna go through it. It's just hard, we could even combine it in one of the other things, but I was just gonna post an assignment and information on it. And then maybe I'll like post questions and ask you how you feel about it. Okay. So this alternate form of the rate equation, oh, let's see, I'm about to turn on draw for this thing. Okay, so here's like this generic, hopefully you're getting used to this thing, this generic form of this equation. Hello, I'll put it in draw. Well, maybe I'm not going to be drawing on it. I guess I can point at stuff. So let me try one more thing. Maybe if I can just make it big and have that. Okay, so this generic form of the, oh yeah, now it wants to draw because it doesn't like to draw in present mode. That's weird. So you're getting used to this, right? Where they call the reactants A and B and the product C and D, and then here they're putting like little letters in front as those coefficients. Like I gave you kind of example here, like it could be 2A plus B goes to 3C and 4D, where you actually have coefficients in front of it instead of these weird little letters. And sometimes they want to give you the rate in this other form. I think we've seen this before. You will see this again in thermodynamics. Do you remember these deltas? The delta is a Greek letter. It looks like a triangle. This means the change in. We'll just call it change. So this is, and now whenever you see brackets around like a chemical or a letter, that means concentration. Maybe I shouldn't try to write everything. I'm going to be slow. Yeah, just make sure that like you really think of things like that. Like you want to have notes to refer to, but like it'd be slow looking every single thing up. So, so then now you can do the rate in terms of this change in concentration. Like here you've got the change in concentration of A over the change in time. And they might want you to compare rates. It's not super likely this is going to show up. I wouldn't make a huge deal about it. I would just understand it. I think it's easier to kind of see how it works with the numbers, which is why I just kind of threw in numbers for the coefficient. Like you can relate the rates to each other. Like the rate is, oh, I didn't include the, that should have been delta over, I guess I did this a little too fast. There should be a little delta here. But the key thing is it should be the change in the concentration of A over the change in time, the change in concentration of B over the change in time. This is important, it's negative. The rate is equal to the negative change in concentration of A because these are reactants, right? You almost always say the rate in terms of reactants. So then those are going to be negative because they're disappearing. It's really important you think of like the rate's going to be negative when the change in the reactants are going to be disappearing, the products are going to be appearing. So the change in products is going to be positive, the change in reactants is going to be negative. So, and this -1/2, and then this would just be 1, -1. Um, see how if there's -1/2 in front of the change in A over time, and there's 1 in front of the change in B over time, see how this one's like slower? This is gonna happen half as fast as B. It kind of makes sense, right? Because if there's a 2 in front of A, there's twice as much of A as B, or twice as much of A is going into the reaction as B. So it's gonna take it longer. It's gonna be half as fast to kind of use up A as to use up B. So anyway, I just want you to kind of have a way to think about this, but you should have this equation there just in case you need it. You probably won't. So, okay, now we're switching over to these integrated rate laws. They basically take these weird, what I'm calling these weird alternate forms. I just call them weird alternate forms because we just don't see them a lot in chemistry. We don't use them a lot. We either use the rate law with the K, or we use the integrated forms. This is just another form that we just don't use as much. But you can take these things, you can integrate it with calculus, you know, the whole deal. Don't think about that too hard because you don't have to integrate it.
When do we use that other equation?
So let me try to find an equation, a problem where they will ask about it. Like if they're asking, it's going to be something where they're asking like how much faster does B disappear than A? Or how much faster does C appear than D? This is only really good if you're comparing it. Or if they show you this form, if they give you like, they give you a like delta A over delta T and they talk about it, then you would have to be able to say something about it.
Okay.
Yeah. Okay, so if you take this previous form of the rate law and you integrate it, because, yeah, like, I don't know. Let's not go into a lot of detail about that, but this is like, you end up, if you graph how, if you graph the amount of reactant A, we'll put it in brackets for the concentration over time, you get these curves. Like it's a reactant, so it's gonna go down over time. You can't find the slope of a curve. You can find a slope of like one point of the curve, like one small little section of the curve, but then the slope's gonna be slightly different. So if you integrate this thing, you can actually get the time for the whole thing. But I wouldn't worry about it. That's why they're called integrated rate laws. They're not gonna ask you about that. So we're basically taking this form that's only really good for one point. We're making an integrated rate law, which is a lot more useful, which is a lot more, this could show up on the test. It did show up on one of the versions of the one that they gave, what was that, a week ago? I can't keep track. The first test for the AP chemistry this year. So you know what orders are now, right? Let me show you. I've got 0 order, first order, and second order. There could be third order, but it's pretty rare, so that it's not even a thing because it's just really unlikely for something to have that order. And so it's really common for them to give you different versions of graphs and to have you use those to figure out which order it is. Like you did the whole thing with the rate laws, or hopefully you've seen that, or make sure you go look at that if you haven't seen it yet. I think you've all done it. And now this is a way, like if you're a scientist in the lab and you have this new reaction and you're studying it, what you do is you collect data, those data tables that have the concentration of the reactants, and the rates, and then they have all the different ones, and you can use it to find the order. They will take all of that and they will graph it in different ways to try to figure out what order it is. And so if it's 0 order, graphing it this way, really pay attention to this, concentration of A versus time will give you a straight line. But graphing it this way will only give you a straight line for 0 order. Let's worry about the half-life expression later, or maybe we won't even, like, it's really just an equation that you could use. We'll talk about that a little bit at some point, but let's really just talk about how to figure out if things are 0 order or first order. Really notice how the y-axis and all these things is changing each time. Right now, they're plotting the natural log of A. Do you guys know about natural logs? Hopefully you've done that. They're not that different than regular logs, and you're probably not even gonna have to use them, but I would just know how to put them in your calculator. Like, just let me know if you have it and I can find some little thing on them. So here they're plotting the natural log of A versus time. And this gives you a straight line for first order. And then second order, you're plotting 1 over the concentration of A, or 1 over the concentration of one of the reactants versus time. So see how the x-axis is always time, but the y-axis is completely different for 0, first, and second order. And it comes from these integrated rate law expressions. And we're going to do an FRQ where you have to look at these, where they give you different versions of these graphs. Like if a chemist has a new chemical reaction they're studying that hasn't been studied before, they will do all 3 of these graphs for, like they will do a table of data where they do the concentrations of the different reactants, and then they'll measure the initial rate of the thing, and they'll do that for a bunch of different concentrations, and then they can make this graph. See, they're graphing the concentration, the time it takes to do the reaction, or sorry, I'm saying this wrong. They're measuring, they start the reaction and they start with whatever concentration they put in of the reactant. This is the beginning concentration, and that is called A sub 0. This is the initial, we'll just call that initial. That's the initial concentration. If they put a little 0 here, that means initial. And so it starts at that initial concentration, and as time goes on, it decreases over time. And so if a scientist has a reaction that they want to study and they want to figure out what order it is in A, they don't have I mean, they could use the table like we do, but they could just graph it. And they can graph the concentration of A over time. They can figure out the natural log of all those concentrations of A. They can graph that over time. And then they do 1 over the concentration of A. They graph that over time. Only one of these will be linear. Only one of these will be a straight line. The other 2 will be curves. And then they'll say, oh, like, you know, if it was 1 over A, that graph that was linear, then it would say, oh, wow, then that must be a second order reaction. Or one of the other ones could come out linear, and then they know that. So let's look at the other things that you get. Here are just that you get in this table. I've got this information sheet. I think it's called a review sheet with all the stuff on it. That's where I got it from. I will put that in Google Classroom. I think we should modify it a little bit so we should definitely modify it so it's a lot simpler, but you can see it, like you can have this as a table, or you can refer to this if you have the stuff show up on the AP chemistry test. So this shows you what order it is. It's 0 order. This gives you the rate law, right? You know that if it's 0 order in A, this is what your rate law is going to look like, at least with A. There might be a B or something there. Rate is equal to K, A to the 0. And anything to the 0 is 1. So really, what this means is rate is equal to K, right? There's the A to the 0 just becomes a 1. And I don't know if all of you have seen the units thing and done that. I asked you to figure out the units of K because the units of K can change depending on what your rate law is. This table gives it to you. So I would know how it works, but at this point, you probably don't want to spend any more time figuring out what the units of K are. You can go figure, but be careful, this only has one of the reactants. If there's A and B, then you have to kind of account for that. But it's nice, it gives you the units of K. Here's your integrated rate law. It's just turned the rate law into something pretty different. I would just know what these things are. A sub 0, that's the initial concentration of A. A sub T is the concentration of A at different times. That's what you're plotting in your graph. And then here's T, we're plotting it against T. And I would think of this in terms of, this is the form that they usually write a linear equation in, y equals mx plus b. You've probably done that in algebra. And well, or yeah, I don't think anyone uses a different form. Let me know if they do, but this tends to show up a lot in math. And this is the same form, right? Your concentration at different times is your y. Negative k ends up being the slope. That's m. T is your x. That's on the x-axis. And here's b, your y-intercept. That's a sub 0. So if you plot this, if you have a bunch of different concentrations in the time and you plot it, that's how scientists can figure out what k is. They can like figure out the rate law from this experimentally. So, and you've got all those things. I'm not going to go through each one for first and second order and stuff. You've just got that same information for each one. The same things show up, like a sub 0 showing up, and t and k. They're just, and k always negative k always ends up being the slope. Is that true? Oh no. See, it's like this is a positive k here. So there'd be all sorts of weird little things to worry about, but you're going to have these in your notes. So, oh, and let me just show you really quick. This is just a quick example of I say zero order graph here, but say like ignoring this and this. Say they just gave you these two graphs. Like, oh, the scientist has this. They have a reaction they're studying. They did a bunch of experiments where they changed the concentration. Or they set it up and they looked at the concentration over time, and then they graphed all of that information in concentration versus time for a reactant, and then they did the natural log of concentration versus time. And a lot of times they'll have three graphs. They'll also do the 1 over the concentration versus time. So they'll have all three options, and then you look at all the graphs. And like if they had this one would be curved as well, because only one of them is going to be a straight line. You look at all three of these, you look and you find the one that's a straight line, and you're like, oh, here's our straight line. You're always looking for a straight line with these graphs. And they would ask you, what order is this reaction with respect to A? And you would say 0 order, because this graph of concentration versus time is linear. I just showed you the part of the table that's relevant, the concentration versus time. This one's linear for 0 order. So then you know. So let me know if you have any questions. Oh, and here's one with first order, right? Like I took this from a thing where it's telling you what they are. But this one, they give you the concentration versus time graph and the natural log of the concentration versus time. And now this one is linear. So you're like, oh, this is linear, therefore it has to be first order. Like, you'll have your table where you can see that one is that when these things are plotted in a graph, that's the linear one if it's first order. Oh, and then I didn't realize I put all three of these. Nifty. So now our 1 over A versus time, now that graph is linear for, say, another reaction where we're calling them all A, just to be like, just give you these general forms. And now since this graph, the 1 over concentration versus time, that's, now it's second order. Okay, finally, here's our FRQ. Can you see that? Should I make it in presentation mode? Looks kind of tiny.
We can see it. Well, I can. Yeah.
Oh, okay. Well, we'll see if I have to draw on it. So at high temperature, so we've got our reaction. At high temperatures, the compound C4H6, which has got a nice name, reacts according to this equation. The rate was studied at 625 Kelvin. Don't worry too much. Oh, I forgot. I'm trying to write on it, but it won't do it in presentation mode. Don't worry about the temperature right now. You might need it later, but sometimes they just like to tell you it's in a certain temperature just to make it seem really experimental, and it might not even matter. They did 2 different trials. The data is plotted in 3 different ways. So I'm just showing you the whole FRQ, and then I'm going to put the 3 graphs in one place. So notice, is my cursor even working? Huh, interesting. I gotta find a better way to do these presentations. So notice that they're plotting the there we go. They're plotting the concentration versus time, That was for the 0 order one. And they're doing the natural log of the concentration versus time, and they did 1 over concentration versus time. And I put all 3 graphs together so you can see them on the same screen. So now you're looking hard at these, and they made the data more experimental, right? Like you see all these different points. Which one do you think is linear? Because only one is going to be, right?
Do you want us to respond like verbally or?
Yeah, or I can just tell you. Well, what do you think? Is it obvious to you?
I think it would be the third one
Nice.
because
Yeah,
the line is linear, it's not curvy.
Yeah, see, this one's like it's almost linear, but it's a lot, and that's why it's good to compare them, right? This one's obviously curved. This one looks like yeah, but you can definitely see a curve in it. But yeah, I compare them all, and then this is definitely the most linear, so you're set. So yeah, they like to do that. They'll give you a set of 3 graphs because that's what a scientist would actually do in lab. They would make the 3 graphs of their data. You find the one that's linear, and you're like, oh, this must be second order in this reactant in C4H6. Oh, and then that's the whole FRQ. Wait, oh, but there were 3 questions. I didn't put them on here. So let me go out of this. Let's go find, oh yeah. And well, we can start, just let me know what you want to do. We can start going through these.
Was that question, like, what was the question? Like, was the question just to look for the linear graph, or?
No, it wasn't. Let me find it because I thought I put the whole FRQ thing on here. Nope, that's the study guide. Where was it? Let me find the, oh, I know. Let me just go get it out of my drive. Let me show you the question because yeah, there's even gas laws in this question. That's what's really cool about starting to look at the FRQs because now, concentration. Oh, there it is. Oh, no, that's my PowerPoint. Let me go. Hopefully I can find it fast. PowerPoint. I just put it in today, so let me check recents. No, I keep finding the PowerPoint when I'm doing recents. Kinetics study guide. And wait, I think it's right here. Aha, okay, so let me share this screen with you. I finally located it. Stop sharing that. Start sharing this. Okay, so here it is. There's all the information you saw. Here's the 3 graphs. Let me show you. There's like answer. Yeah, so these are like people's answers written in. So you can look at those if you want. But here's the 3 questions. For trial 1, calculate the initial pressure in atmospheres in the vessel at 625K. So this, they've actually like thrown in gas law stuff here because you're supposed to calculate a pressure in atmospheres. You've got a temperature and assume that initially all the gas present in the vessel is C4H6. So how are we going to calculate what other, oh, and you have the temperature, yeah. It looks like, so yeah, do you remember this gas law stuff? Remember, this is open notes, so you just wanted to have enough of that gas law stuff written down that you can go refer to it fast. Do you need to use PV equals nRT, or do you need to use, because, oh, they tell you 625 Kelvin here, like they do in the initial part of the question. And we know what R is. And we have to calculate what P is. And do they tell us anything about the volume? No, we don't know anything about the volume. Let's go cheat and see. N over V. Where do they get 0.02 moles from? Oh, wow. So oh, they're finding it from the graph. Yeah, so there's just different way. If they give you graphs, they might want you to get information out of it. Like they tell you to calculate the initial pressure in atmospheres in the vessel. So initial pressure, that's at the very beginning. What's the pressure at the very beginning? The very beginning of the reaction, there is 0.02 moles per liter. So they're saying, okay, let's just say we have 1 liter, because they don't tell us how much there is, right? And that means there's 0.02 moles. So then you can do PV equals nRT, because you have 0.02 moles, you have 1 liter, you have 625 Kelvin, and you have R. So then the only thing that's missing is P. So, but see how you have to be on the lookout if pressure and temperature and volume start showing up, then you should think about the gas laws. Because you can tell this is kinetics. You can tell that this is like the concentration versus time and graphs you would recognize. It might be a little harder to recognize that this wants you to do the PV equals nRT stuff. So that's the key thing. Those are the skills you really have to think about for this test. And like I said, I'll share this with you so you can look at this, like see how they put in 0.02 moles and 1 liter. Like you don't think at first about separating that. You know you have 0.02 moles per liter, but you've been thinking about those as conversion factors, so you can take those apart. And here's your R for the gas law, and here's the temperature, and then they solve it, and it's 1 atmosphere. And one of the other things that's going to be really good for you to see about those 2 versions of the AP chemistry test that they just gave for this year is there weren't very many calculations. There was just a little bit. They're not going to make you, they would have made you calculate a lot more, but with it all being online and it being fast and you having to upload stuff, then I think they made you do 1 calculation on the one that I looked through really carefully, but I didn't really go through and like check it all out. So what else do they ask you for? Use the data plotted. Oh, go ahead.
I just have a question on how you knew to check the first graph that they give us.
See, like
I understand like we get 0.2 because it says for trial 1, but
yeah. It's from initial pressure. So
all the graphs, like, don't they all have like their own like initial pressures?
Yeah, but they said trial 1 and oh, so you can only take it from this graph because natural log of concentration doesn't make any sense when we're trying to do the gas laws, right? Concentration makes sense because concentration is moles per liter. This natural log, see how it doesn't even have units?
Yeah.
Like when you take the log of something, there are no units. It's like the log of 10 to the minus 2 is 2. There's no units for that. And see how this one doesn't, well, this one has units, but well, you could do this if you could do it from this one if you really wanted, because you could say trial 1 is this one. You could say 50 liters per 1 mole, and you would get exactly the same answer as if you said 0.02 moles per 1 liter, and they would be fine with that. As long as you do something that makes sense chemically, you'll be fine. So does that make sense? You have to use this graph or this graph because you kind of have to do it according to units. You have to say 50 liters per 1 mole.
So we wouldn't get a different answer if we used
No.
the second one, because it has a different initial pressure, right? Because it has, for trial 1 it's 50.
No, but the trial 1 means experiment 1. That was the first experiment they did. It has to be the same because it was the same experiment. So if they had 50 liters in 1 mole, and if you do 1/50, you get 0.02. So if you, and look at how you put it in, and then, yeah, just convince yourself. Like, what you have to do on the test is find the information, find a place where the information makes sense and use it. And maybe a different version of the information will show up somewhere else that you could have used. But see, if you take the first graph, you'll have 0.02 moles over 1 liter. If you do the third graph, you would have 1 mole over 50 liters. Use your calculator. 0.02 divided by 1 is 0.02. 1 divided by 50 is 0.02. So see how the numbers will come out exactly the same. And this is, in a way, this is nice because this is more like real science than a lot of the tests we tend to give you in school. Like, this is something a scientist would actually do. They go and find information in different ways. Like, one scientist would do it one way and the other would do it the other way, and they're both totally, they come out the same, as long as what you're doing is correct. So right now, let me find a normal thing for the questions. Use the data plotted in the graphs to determine the order of the reaction with respect to C4H6. I think we did that. We decided it was second order, right? Yeah, because this was the linear one. The other two were curved. So we decided it was second order with respect to C4H6. And one thing to really think about this, like in school, you're just so used to going sequentially through every one and working really hard to finish everything because you're supposed to finish everything on the tests in school. We tend to think you're just slacking off and not doing all the stuff if you don't finish everything, because tests in school are designed to finish it all. This test is not designed. They are expecting, like, I don't know, 90% of the people who take this test, maybe almost 100%, not to finish this test. And it's just a matter of how much you finish that determines your score. And really believe that if you get 75% of your test correct, you will get a 5, the top score. There's no difference from somebody who got every single question right and somebody who only got 75% of the questions right. So if you're like, oh my gosh, I don't know what to do with this one, but you go to B and you see how to do that, you should go work on those things and then look back at A and think, okay, do I see anything that it's doable? And if you don't, I would just keep going because you'll still get a really high score. The way to destroy your score is to get stuck on something. You're like, I don't know how to do this. You're flipping through your notes and you're wasting all this time and you still don't get it. Or maybe you get it, but you wasted way too much time on it.
Sebastian's asking to be let in. I don't know how he
got. Oh, maybe it bumped him out. Thank you. I'm not looking at that thing. Let's see, let me get rid of all this stuff. And more. Oh, there's participants. Okay. Oh, good. He texted you or something. Nice. And okay, so, and then you would just explain this, right? And that's the thing. I'm going to put an assignment up for you. There's a place you can go, I guess an AB Classroom or something. I've got a link for it where you can, I'll put that in right away. You need to try out uploading answers. There's 2 different ways you can do it. You can type it out in something like Word or Google Docs or something, and then copy and paste it into the test, into the online test, or you can take pictures of, you can write it out and take pictures of it and then take a picture of that and upload it, but you need to think, is it going to be slower to write stuff? And I'm pretty sure you can do a combination of the two. I want to see if I can go try uploading it. So you want to think about how you're going to be putting your answers into. Let me make myself a note that I'll put that in. Okay, so and so you would just explain this, right? You would say, like in looking at the three graphs of the data, you would just say like the graph of concentration versus time is not linear. The graph of the natural log of concentration, and you can just write ln like with the brackets and stuff like this. The natural log of this concentration isn't versus time, that graph isn't linear, but the graph of 1 over C4 H6 concentration versus time is linear. And I would even say something about the equation, like therefore it matches a graph of the equation. You can do that. Yeah, see how they give the equation here from the second order rate law integrated form. You can say the integrated law. You could just say the second order rate law. You don't have to include every word. Then we can see that it's second order. I wouldn't include all this coefficient of t is equal to 2k. That's how these answers can really freak you out. That's why it's good to see different answers. I'll give you this one so you can look at it. But the key thing is they just ask you, yeah, see, this person says a lot less. The plot of this versus time shows a linear relationship indicating second order. That's what you really need to, yeah, you might not even want to spend a bunch of time saying the other two aren't linear. You don't have to like say which ones they are. And so this last one, the initial rate of the reaction in trial 1 is 0.001 mole per liter second. Calculate the rate constant K for the reaction at 625K. So you've got to show the steps. So it's good if you do that at least once. And then you obviously want to put in your units for K. Here you can just go look them up in your table because you'll have that as the notes you're referring to. I think you should. And let's, yeah, I want to like give you notes and just give you really organized notes, and then you can make, I want to give you printouts of those, or if people can print them themselves, we'll just figure out what works best for everybody. And then I need to give you the notes for this one like in the next couple of days, so that I want you to start, you can add extra notes, you can personalize them. So you're really familiar with them. It has all the information the way you want to see it. And then you know you're referring to those during the test. So because you can even just go find the units for K. You don't have to go figure them out on your own, because remember that was in that table that I was showing you the different parts of that table. And so, yeah, you've done this before. Do you have any questions about, like, here's somebody, they wrote it out. Oh, they're figuring it out. Oh yeah, they're just plugging it in. It looked different to me, but yeah, you have your rate law, and that's what's nice. Like that'll be there right now. As soon as you know it's second order, you can look at it, or you just know rate is equal, it's always K, and then you have all the different reactants. They're only talking about one, so there's only one. I think there was another one in this, but we just ignore it because we don't have information about it. Where'd our little reaction go? Oh, there was only one reactant, so you only have to worry about it. Because remember, all the reactants are on that rate law. And so as soon as you know it's second order, you move on to part C. Rate is equal to K. You know that this reactant is second order, so this concentration to the second power. And then you just plug things in. And then here they're just showing their work. They're putting the numbers in and canceling out the units and stuff. And then showing the final answer. I'd put a box around your final answer just so it's super clear, because here it's pretty clear. There's no uncertainty, but it can't help. I'm in a group where some of the people who actually grade these exams are, and they say if there's any uncertainty about the answer, they'll choose the one that has a box around it if they do. So I would just get in the habit of doing that just so it's like 100% sure what you think your final answer is. So yeah, so this is like a more typical FRQ. It's got these 3 parts. Just don't be freaked out when there's like a trillion parts. I think it was kind of a weird thing for the College Board to say there's only 2 FRQs. And then they seriously have like parts like A through G and A through L. And they did that on all of them. So is there anything else we should talk about now?
Amy,
Yes.
I have a question. So when you say that it's from A to L or A to E, is it per FRQ?
Yeah.
So how many FRQs are going to be on the test?
There are 2.
What?
And
There's only 2 FRQs?
yeah, but it's not with 3 parts. Like this is an FRQ, but it's with 3 parts. Here, let me bring that up. That should be pretty fast to find. I can just show you this one, and I'll put it in Google Classroom. It just looks really, really long. That's why I would get yourself in the habit of just look at things, see it, figure out how to do it. If it's not immediately obvious, just start moving through and finding other things to do. Exam resources. Okay, here's FRQ. Here's the exam version 1. Let me see.